Hello, I'm Carlos Suarez and this is the CRS channel. This is the first video in relation to physics problems, in this case problems in kinematics, basically motion in one dimension. First problem is the following. A rock is thrown upwards with speed v from the edge of a cliff. A second rock is thrown vertically downwards with the same initial speed. Which rock has greater speed when it reaches the bottom of the cliff? Ignore the effect of air resistance. Here we have a sketch. This is the edge of the cliff. This is the bottom of the cliff. H is the altitude from the edge of the cliff to the bottom of the cliff. This is the rock that is thrown upwards with velocity v. This is the rock that is thrown downwards with velocity v. Okay, so this is the equation for the velocity of rock 1 that is thrown upwards. This equation corresponds to motion with constant acceleration. So the velocity of rock 1 equals its initial velocity minus gt, which g is the acceleration of gravity. Position of rock 1 is given by the expression h plus vt minus 1/2 of gt squared. This corresponds to the case of constant acceleration. H is the initial altitude, v is the initial velocity, and g is the acceleration of gravity. Expression for the velocity of rock 2 is minus v minus gt. The expression for the position of rock 2 is h minus vt minus 1/2 of gt squared. Okay, so to determine the speed at which each rock reaches the bottom of the cliff, we have to find the time at which each rock reaches the bottom of the cliff. Once we found time for each rock, we can replace such time in the expressions for the velocities. So in the first case, when we consider rock 1, this expression is equal to 0, which is the position corresponding to the bottom of the cliff. So the position for the rock when it reaches the bottom of the cliff will be y1 equals 0. So h plus vt minus 1/2 of gt squared will equal 0. So we have to solve this quadratic equation, and the solution for this quadratic equation gives us this expression for t. Remember, if y is a function of at squared plus bt plus c, the solution for the equation at squared plus bt plus c equals t is t equals minus b plus minus the square root of b squared minus 4ac, all that divided by 2a. So we get this expression. which can be simplified to this expression here. Now, since the time has to be positive and this expression here is greater than this expression here, the term in which the sign before the radical is minus is not considered for the solution of the physics problem. So we are only left with t equals v over g, factor of the expression within the brackets, which is 1 plus the square root of 1 plus 2gh over v squared, which gives us this expression here. V minus equals v minus v times the square root of 2gh over v squared, and in the end it gives us v1 equals minus v times the square root of 1 plus 2gh over v squared. So this is remember, I have replaced this value of t in this equation here, in this expression here, and this is the result. The velocity of rock 1 when it reaches the bottom of the cliff will then be this. v1 equals minus v over the square root of 1 plus 2gh over v squared. Doing the same thing for the position of the second rock, we obtain this expression for the velocity, for the time it takes for the second rock to reach the bottom of the cliff, which gives us in the end this expression here. Replacing this time in this expression, we get this value for the velocity of the second rock when it reaches the bottom of the cliff. Now, if you see carefully, the two velocities are the same. They have the same sign, which means that they are going in the downwards direction. So, no matter if this is thrown upwards or this is thrown downwards, the two rocks end up reaching the bottom of the cliff with the same velocity. Now, the two times, of course, are different. This time, for the rock that was thrown upwards, well, it is greater as it was thrown upwards. It is greater than the time for the rock that was thrown downwards. Okay, now the second problem will be solved partly or partially in this video, and the solution will be continued in the next video. In the second problem, we have a diagram that illustrates that a ball is being thrown upwards with a speed v sub 0 upwards from a height y sub 0. This is a position versus time diagram. Y is the vertical position. The ball reaches a maximum altitude and then falls down to the ground and bounces upwards again, reaching afterwards a new maximum height, which is lower than the one the ball reached before. So in this case, we're going to analyze the motion of the ball for different positions. Position A, position A1, position B, B1, C, D, E, F, G. And we will also need to know about this new altitude H prime. H prime. The altitude at which this position B is, or value of this position, will be denoted as H, capital H, or upper score H. Okay, so first we have to write down the equations of motion for the ball. This is also a case of motion with constant acceleration. So we write down the equations: y equals y0 plus v sub 0 t minus 1/2 of gt squared, and v equals v sub 0 minus gt. So those are the equations for the position and for the velocity. So we can rearrange terms here for the case of this equation for the position, in which we add a term, which is this one. We have passed y0 to the side and added this term to both sides of the equation, so that we can complete squares, the square here. So we have minus g factor of t squared minus 2v0 over g. If we pass the 1/2 of g to this side, we'll cancel the g and the half and the minuses and be left with v0. So we have t squared minus 2v0 over g times t plus v0 squared over g squared. And on this other side, which would correspond to y minus y0, so if we added, here we have a negative multiplying this positive, we have a negative multiplying this positive. So we've added the same expression to both sides of the equation. So simplifying here a bit, knowing that this is the square, this expression here corresponds to the square here. We'll leave this as it is. We have the equation of a parabola, for which the vertex of this parabola corresponds to this point given by these coordinates. This is only a parabola for this diagram, not a parabola for the motion. Okay, so we continue in the next video.